Energy diagrams are a graph. One way to think about them is that they're a graph of a potential energy function as a function of the position coordinate of interest. So let's look at gravity. The simple formula for gravitational potential energy is mass times free fall constant times the height, or times the y position. This is assuming a system where up is positive. If we do up being negative and down is positive, then you need to put a minus sign into the formula here. What does this graph look like? So all the energy diagram is, in its most simplest form, is just a graph of potential energy as a function of location. And it's going to be a straight line, pretty much. Right? Yeah, it should just be a straight line. The slope of that line, I'll draw a little bit bigger. The slope of this line right here it is equal to the negative of the force, which is just mg, right? The slope of this line is mg, but since the force is negative mg, the minus signs cancel. Like I said, in work and potential energy, there's this minus sign that you have to keep straight. And I want to, before returning to this potential energy, I want to spend just a minute or two just reminding us about this negative sign issue, okay? Again, in the context of work and energy and potential energy, in general, right, the work done in a single direction for a variable force is the integral of that force in that certain direction at times the magnitude of the displacement integrated over the force. Okay, this is the definition of work. Well, we established that if you integrate this thing, you get two numbers, right? And we showed that for a conservative force, that's equal to minus the change of potential energy. And just so we're clear, let's think about gravity to just justify this minus sign, okay? You drop an object, gravity does positive work, but potential energy goes down. So potential energy decreases as you're doing positive work. Now you toss a ball up into the air. Potential energy increases, but since it's moving upward, right, gravity points down and the displacement is upward. And so the work is negative. And so since the work is negative, then potential energy increases. So there's this perpetual minus sign relating force and potential energy. The fundamental theorem of calculus takes over, and you're able to show that this F sub s, the component of the force in the generic s direction, in order for this equation to be true, it has to be equal to minus the derivative of the potential energy in that direction. And so this equation is why we get the slope, right? But you could have known, you would have known that the slope was equal to mg anyway if you just took the derivative, but there's this extra minus sign that we need to take into account. Oftentimes, potential energy is not just a function of one position, it's a function of all three. And so if it's a function of all three, then we need to take the derivative of this potential energy function in all three directions. And I think in an intro physics class, at least physics 313, certainly not required to be taken or have taken calculus 3. Most of the time when people take physics 2, they've gotten to that part, but so we're not going to mention any of the details about the partial derivatives here. Okay, so that was a brief review of why the slope is negative of the force, right? Because the force is negative, so the slope is positive. So we don't want to miss that opportunity. Now looking at the equation itself, or the diagram itself, what's the point? Okay, so we know the graph. How do we use it? We have to first consider a certain mass. A certain massive object might have a certain total energy, which we call TE. there. Next up. And so in the absence of any dissipative forces or external forces, the total energy of the system stays constant. That's should be a straight line. I'm trying my best. And so imagine if you bounce if you drop a tennis ball and there was no friction or no air resistance or no energy lost by it colliding with the ground, it's just going to go back up to its initial height, and it'll go back down and go back up for, forever, right? I mean, you can imagine that picture. Of course, real objects will eventually come to rest on the ground. But what this shows us is that if the total energy is constant, then we're always going between a potential energy right here, and that's it should match up with the line. But then there's a kinetic energy graph, or kinetic energy, that is minus the potential energy. So those two balance out. And what we see here is that you can never have the potential energy greater than the total energy. Okay? And in general, the potential energy always has to be less than or equal to the total energy. Okay, why is this true? Write that a little bit cleaner. Why is the potential energy required to be less than or equal to the total energy down here? Well, if it was bigger, then that would make kinetic energy negative, right? And when you think about kinetic energy being square root, or when you think about speed then as being square root of 2k over m, now you'd be taking the square root of a negative number. And there's no instance I've ever seen where we treat velocity as imaginary. There's some quantities in physics that make sense to treat them as a complex number with at least this imaginary part, but it's not speed. So certainly not speed in that case. And so that means that graphically that this turning point, or that the intersection of the dotted line representing the total energy with the potential energy function, this thing right here is called it's called a turning point. Right? Because it's not possible that the potential energy, that we're in a location where the potential energy is larger than the total energy. So this, I'll finish writing that out, and then I'll make a remark that may show up in later classes for some of you. So this region out here, we actually do call it the forbidden region, because classically the particle is not allowed to be measured in that location. So that's the forbidden region, where the energy is bigger than, where the energy happens to be bigger than the total energy. That's just, that would be like saying that well, I can give you another example with a harmonic oscillator in just a second for this mass on a spring. So yeah, in the context of a mass on a spring, the potential energy is equal to 1/2 kx squared, where I'm defining x not to be just the position, but x is the displacement from the equilibrium, which I set at the origin. So that's a parabola. Right? And so when we draw the parabola, when we draw the parabola, then now you can show that once again, if the thing has a total energy, then it's stuck in what we call a bound state. It's stuck in a well right here, and it can't get out right here. And so that means that these two, on this horizontal part, which is an actual position, it's stuck between these two turning points. And so if you draw like a thing under it, right, the block can be right here and it can also be here. And it's just going to, you know, oscillate back and forth between the two. So those are the two turning points. Once again, it's where the total energy equals the potential energy, right? And at those points, the kinetic energy is zero because they're equal. So how useful are these energy diagrams? These initial ones, the ones that we're learning about, you know, gravitational potential and spring potential, perhaps they're not extraordinarily useful. It's a easy graphical way for us to go from one spot to the next and show how the speed changes, that's for sure. But the utility of these energy diagrams really comes when you have a more complicated one. So I want to give a couple of examples of a more complicated energy diagram. And one that's actually very, one that's actually very important. So oftentimes, let's say you have two atoms that bond together, either ionically or covalently, to form a bond. So what does that potential energy function look like that makes those two things bond? Okay, we're by no means in a position to explain the, you know, chemistry or even the electricity behind these things, but let's just consider hydrochloric acid. Right? It's a simple example of a molecule, and chlorine atom is so much heavier than hydrogen atom that it's pretty safe to assume that the chlorine atom can be modeled as being at rest. And so you have this hydrogen atom, which of course, you know, we're in 3 dimensions, so the thing can move around wherever it wants. But if we're just considering motion along a single direction, which we might just call R, then the potential energy function of the hydrogen atom, because these are two particles. These are two particles in the context of Newtonian physics. These are just two particles that feel forces around each other. Where do those forces come from? That's not really up for discussion right now. People have questions, I can certainly explain it, but yeah, these are two particles that this smaller dot particle is feeling a force from the larger particle. The formula for the force is very complicated. Not that complicated. But the shape of the potential energy function looks like this. So as you get closer and closer to the chlorine atom, it becomes nearly infinite. And then the further away you get, it dips down to some minimum, and then it drops down to 0. This may actually be a potential energy function that you have in a chapter 10 homework assignment. What does this look like? This potential energy function looks like as a function of R. We like to do R. It's 1 over X. 1 over R. It's 1 over R minus 1 over R squared with units. So to make this, you know, physical, we usually need to add units, and the lazy way that us who teach physics do it would just be to give it 2 letters. So AR minus B over R squared. You have more examples in your homework. Where A has units of, let's see, it would be joules times, it'd be energy times length, right? And then B has some constant that has units of energy times length squared, energy times area, for what that's worth. So what happens is the energy of the hydrogen atom, the total energy of the hydrogen atom will affect what happens to the system. So if the total energy is less than 0, right, because this is potential energy, but if its total energy is less than 0, then it's going, well, it must be less than 0, but it must be greater than this minimum here. Again, you can't have, just like you can't have a potential energy be greater than total energy. You can't have total energy be somehow less than that, because the same thing would happen. You'd have a negative kinetic energy. So basically what I'm trying to say is that if it's got a total energy that is just the right amount, right? You put a bunch, how do these things bond together? How do you make hydrochloric acid? You make hydrochloric acid. I mean, people like to, oh, what's that company's name? Vulcan Chemicals. Yeah, Vulcan Chemicals does that on the southwest side of town. They take table salt, sodium chloride, mix it with water, and you get sodium hydroxide. I don't want to turn this into a big chemistry lecture, but you get sodium hydroxide for one. The other product that is formed is hydrochloric acid. And they also do some other techniques to form like chlorine and all these other, they're a chemicals company. And so these are the types of things that they do. But so in this mess, in this soupy mix of chlorine atoms and water molecules and sodium ions and all these things are dissociating, well, this hydrogen atom is kind of ionized and it's kind of traveling around, somehow maybe got dissociated from water molecule. So the water was dissociated into hydrogen and hydroxide, OH. And so if it has just the right energy, it'll get stuck into the well of the chlorine atom. And so that will make it have an energy like this. These pictures certainly aren't to scale. They don't oscillate that much, but when it's just the right amount of energy, which by the way, the energy of these is usually associated with the temperature of the substance. So a lot of these processes have to be at the right temperature for the stuff to occur. That means that the hydrogen atom is now stuck in the potential energy well, we call it a potential energy well, of the chlorine atom. And so look what happens here. And this is roughly the formula of the potential energy for the chlorine atom. What causes the chlorine atom to have this potential energy function? Just gotta wait till physics 2 to get some context of it. But yeah, so if the hydrogen atom it gets too close to the chlorine atom, okay, the slope of this potential energy function gets very largely negative, right? Which is going to make the slope, or which is going to make the force a large positive force. And sometimes we call these things a van der Waals interaction. On the other side, you have, if it gets too far away, now this negative slope will kind of slowly draw the hydrogen atom back in, right? This positive slope right here will give a negative force. That's the correct way. And so eventually, if the total energy is less than 0, this is one of the turning points. And it doesn't really have a turning point on the far end, but it'll always kind of go back to its spot. Eventually, the turning point will depend on the energy, but this is the absolute turning point that it has to have to stay bound. Other place it'll just go back, and so it'll just sit in there, and you can give it energy, and in fact, very the lowest amount of energy that it can have and stay bonded is actually not the very bottom. It's very close to the bottom, and there are these so-called rungs of these ladders of the allowable energies of the hydrogen atom inside the chlorine molecules, chlorine atoms, sort of influence of potential energy. And these things kind of go up, and the energy more or less increases at a constant rate. If the total energy is bigger than 0, here you have what's called a bound state, where the energy, or where the hydrogen atom is stuck to the chlorine atom, and it's bound. Right? Now, if the total energy is greater than 0, then you can see here that it can be infinitely far away and still have a non-zero energy, right? Because that, if you gave it more energy, say you shined a specific frequency of light on it, or you heated it up, and eventually the energy of the hydrogen would be so large that it would pass this 0 threshold, and if the energy's up here, well then, now the thing is free to escape not the gravitational pull, but escape the really electric pull of the chlorine atom. And so this is certainly an example that is worth going through. In fact, you can use basic calculus to find the location of the minimum of the potential energy function. Just by taking the derivative of this thing, you'll get, what do you get? The derivative would be, well, it would be the place where the force is 0, of course, which is at the very bottom, and then associate that with a specific value of r. We call it r sub 0. Yeah, let's call it r sub 0 actually, because if we call it r sub 0, then that would be the expected distance of the chlorine atom to the hydrogen atom, and that is typical bond lengths, which are on the order of angstroms, if I'm not mistaken. Right, so if you can take the derivative of that thing, we don't really have to. Might even be a homework question down the road. You can find that value, and that's a way to estimate the sizes of these things. Oftentimes, in realistic experiments, they might take this atom or take this molecule and somehow measure this to find these constants, find A and B. And this is for very simple diatomic molecules. Not diatomic in the sense that they're the same, but just 2 atom molecules. And it's really interesting when you look at it because that's how all molecules form. All molecules form by the other atoms creating a potential energy function around them such that if the next atom comes in, it's stuck in that specific spot. Take a look at, what about carbon dioxide, right? We took carbon dioxide, this carbon dioxide part, right, might bond with an oxygen part, and so that shape will also be the same sort of thing. And so that oxygen atom will be stuck right there. These are only one-dimensional things. When you get to like two-dimensional, molecules, or even if you start to get to these like carbon rings, it forms according to the lowest energy. And that's a real general principle of physics, is that systems will arrange themselves in the lowest energy. So although the energy diagrams that we do in this chapter aren't necessarily the most complex ones, we will get to ones that are a little bit more confusing in later chapters.